Hello, in this video I'll show you how to create dynamic rain, complete with collisions, splashes and wind. So after briefly getting inspired by the Dutch weather, set your frame rate to 60 or 30, 24 won't work. The render engine doesn't really matter, but I'm gonna be using Eevee because it's faster. Start by deleting everything, adding a plane and then scaling it up. Open the Geometry Nodes tab and add a new tree to the plane. You can call it whatever you want, but I'm gonna call mine rain. We need some points to work with, so add a distribute points on faces node. Now we need to make our points move, so add a simulation zone that will update our simulation every frame. If you click play, you notice that nothing's gonna happen, so we need to add gravity to our simulation. When making something using simulation nodes, you have to follow one rule that what goes out must come in. By clicking on either of the simulation nodes, add a new socket, call it velocity, and switch the type to vector. Now, we're gonna need to update the position of the points, and we can do that with the set position node. By adding some offset and clicking play, we can see that our points move by the amount we defined every frame. So let's make our offset gravity. Add a vector and set the z value to -9.8 and plug it into the offset. Now our points move almost 10 meters a frame, and that is way too fast. Fortunately, we can fix this by scaling our vector with the delta time. By doing this, we move the particles every second, not every frame in our simulation. And now our points fall at a reasonable speed. Currently, the points travel at a constant speed. We can make them accelerate if we add the previous frame's velocity to our current one, and then plugging it back into the velocity output. And since our velocity is in a loop now, we can just plug it into the offset directly. Now our particles accelerate very quickly, so let's scale the velocity with the delta time again. Now we have points falling at a convincing speed. Our points get generated only on the first frame, so let's add some more. We can do this by joining geometry from our distribute node straight into the simulation zone. Now we get new particles every frame. It would be great if all of our points didn't look the same, so let's add a seed to our distribute node. By far the most convenient way to do this is to add a scene time node and plugging in the frame into the seed. Now we will have a different seed every frame. Now we have something more closely resembling rain. Since all of our particles have the same starting velocity, we eventually get this layering effect. So we need to give every particle some initial random velocity. We first need to add a random value node and set the type to vector. Then plug in the random value into the velocity input of our simulation zone. We don't really need randomness in the lateral direction, so leave only the z direction random. To give every new point some randomness, we have to add the random vector with the velocity in the simulation zone. This gives us a very chaotic result because we're applying the random velocity to every point, every frame. By using a capture attribute node and setting its type to vector, we can now capture the random velocity of each new point without compounding it. Make sure to connect the distribute node through the capture attribute and back into the join geometry and remove the old link. Now we have points that fall like rain. Right now there's too many of them, so let's change the density on the distribute node to something way lower. It is also useful to increase the amount of frames in your scene to have the simulation run longer. Currently, our points keep accelerating indefinitely, so we need to add a terminal velocity to them. According to these guys, rain only falls up to a maximum of 10 meters per second. We need to add a maximum node right before plugging it back to the output of the velocity, and setting the maximum velocity on the z-axis to -10. Now our points have a maximum speed which they fall at. We're done with our falling rain, so let's add some collision to it. Let's move our points up and add a new plane below them. On the plane, click M and move it to a different collection. It's gonna be our collision. Back in our node tree, let's add the collection by using a collection info node, then selecting the collection and setting it to relative. We need to turn the collection to an actual mesh, which we can do by using a realize instances node. The mesh needs to be there because we will be using a raycast node to detect the hits. We're gonna add a raycast node and plug in the realize instances into the target geometry socket. Back in the simulation zone, let's add a delete geometry node. Then plug in the raycast is hit output into the selection of the delete geometry node. If you play the simulation out, you're gonna see nothing because our raycast is way too long. So set it to something lower like 0.4 meters. Now if we play the simulation, we're going to see that the points disappear just above the ground, and the distance between the ground and the particles is the distance we set the raycast length to. However, decreasing the raycast distance will not solve the problem, as the particles will just fall through the floor. We currently shoot the raycast down from the particle to the floor. We can also do the opposite and shoot the raycast up to detect a collision once the particle is just below the plane. In what I like to call a classic Blender moment, by shooting the raycast up, the particle gets deleted right at the plane. To implement this, we need to change the raycast ray direction on the z-axis from -1 to 1 and change the ray length back to like 0.4. Now the points get deleted right on the collision plane. Now we have a system that can interact with any object in the collision collection. We're going to use the output of the rain system to create the splashes. We need to set the splashes where the rain gets deleted. So take the geometry output from the set position and place it into another set position node. Then take the isHit parameter from the raycast node and plug it into the selection. Then do the same with hit position. Now, if we plug in the new set position node into geometry output, we can see that the rain sticks to the collision objects. So far our splashes are just points on the ground, so let's add some geometry to them. Let's do that by plugging in the set position output into instances on point node. As the instance for the splashes, I'm going to be using an n-gon mesh circle, but you can really use anything you want here. We really want to have the splashes as a separate output, so in the simulation output, create a new geometry output and call it splash. Outside of the simulation zone, we want to join the geometry of the rain and the splashes together, so we could see it in the viewport. Now we see the mesh circles on every rain point, and to make them appear only on the ground, we need to take the raycast isHit output and plug it into the selection of the instance on points. Now the splashes appear where they should, but they're average sized, so let's lower the mesh circle radius to something like 0.1, and to make the simulation run smoother, the resolution to 12. Now we have created the splashes. However, we still have frozen rain points on them, so we need to delete them. Fortunately, we have already done that. In the simulation output, add another geometry output, and call it rain. Plug in the delete geometry node into the rain socket, and then join it with the rest of the mesh. We also don't want to join the standard geometry output now. You might notice that your simulation now is broken, so just make sure that it's the first output in the simulation output node. The points on the splashes are now gone. When rendering in Eevee, we cannot see anything, so let's add some meshes and materials for our simulation. Let's plug in the instances on points node into the rain output. As the instance for my rain, I'm going to be using an icosphere. I'm going to scale it down less on the z-axis to give a motion blur effect. By using the set material node, we can give the rain some color. Since I'm rendering in Eevee, and I want a more stylized look, I'm going to give my rain some emission, then assign the material in the node tree. Now that the rain is done, we can add the material to the splashes too. Duplicate the set material node onto the splash output. For them, I'm going to be using a blue emission material. And now we can see our rain and splashes in the rendered view. In our simulation right now, the splashes keep accumulating, and we need to delete them with time. Unfortunately, Blender does not have an age node, but we can make one ourselves. Start by adding a new simulation output and setting the type to integer. Let's call it age. We need to know the age of every splash, so add a capture attribute node between the set position and instance on point node, then set its type to integer. For the attribute input, we can plug in the age from the simulation input node. From the capture attribute output, add a math node and set it to add +1. Then plug it into the age on the simulation output node. This setup will allow us to know the age of the splash, and it will also be increasing the age by 1 every frame. We now have the age of each point, so let's delete them depending on how old they are. Start by adding a delete geometry node, and place it after the capture attribute. And by taking the age and plugging it into a greater than comparison node, we can decide which particles get deleted. By setting the greater than value to 50, we can delete points that are older than 50 frames, by plugging it into the selection socket of the delete geometry node. Now all that's left to do is plugging the delete geometry output into the geometry output of the simulation node. If the splash deletion is not working, make sure that the age socket is below the geometry socket in the simulation output node. And if the rain particles get deleted midair, just increase the age on the greater than node. Now we have splashes that disappear. If we rotate any of the collision objects, we can see that the splashes don't rotate with them. Fortunately, this is a very easy fix. We just need to take the hit normal from the raycast node and plug it into a line Euler to vector node. Now you can plug in the rotation into the set instance on points node and switch the axis to Z. Now we have splashes that dynamically rotate to the collision surface. If we go into rendered view, we can see that our splashes are glitching. That is because they're right on the collision plane. So we need to move them up just above the collision surface. After the instances on points node, let's add a set position node. By increasing the Z offset, we can see that all of our splashes move up from the surface. However, this is not a great solution, because on curved surfaces, the splashes would just move up, and we want them to move outwards with the rotation. To offset our splashes with the curvature of the collision surface, we first need to take the velocity and normalize it to give us some numbers we can work with. We then need to multiply the normalized output and plug it into the offset of the set position node. From the raycast hit node, let's take the hit distance and plug it into a subtract node. Then plug in the subtract node into the vector multiply. By changing the value on the subtract node, we can add an offset to the splashes from the surface, with the direction of the surface hit. I added some lights to the scene. If we want a wind effect in our simulation, we need to go back to the gravity vector. And by changing the x or y values, we're gonna get some wind. Unfortunately, all of our splashes are gonna be going the same direction too. So let's take our velocity and plug it into a vector multiply node, then set all the vectors to -1, since we still want to shoot up from our point, not down. We can then plug in the multiply node into the ray direction on our raycast node. Now our splashes don't slide around. For the last step, we need to get the rain pointing with the wind direction. So let's take our wind/gravity vector and plug it into the simulation node output. I'm gonna call it rain rotation. For the final step, we're gonna be taking the rain rotation vector and plugging it into another align Euler to vector node. What's left to do is to plug the rotation into the instance node and set it to Z. Now our rain actually rotates with the wind. So there you have it, a fully dynamic rain setup using simulation nodes. I hope you learned something new, and thank you for watching.